Hello and welcome to Bedtime Science. Before we begin, take a moment to like the video, subscribe to the channel, and let me know down in the comments where you're watching or listening from tonight. Whether you're in a quiet city apartment, a countryside home, or somewhere far across the world, it's always a little fascinating to think that, at the deepest level, the same strange quantum rules are quietly unfolding everywhere. Beneath your room, beneath your thoughts, and beneath everything you can see. Tonight, we're going to explore a question that has puzzled scientists for over a century. Why is quantum physics so strange? At first, the world seems simple. Solid objects stay where they are. Causes lead to predictable effects. Things exist in one place at a time, moving along clear paths from one moment to the next. This is the world we experience, the world our minds were shaped to understand. But as we gently shift our attention inward, toward the smallest scales of reality, something begins to change. Particles don't behave like solid objects. They don't follow neat, predictable paths. They don't even seem to exist in definite states until something interacts with them. Instead, they blur, spread, and exist in multiple possibilities at once. They influence each other across vast distances, and they follow rules that feel less like the motion of objects, and more like the unfolding of probabilities. It's not just unfamiliar, it feels almost unreal. And yet, this strange, quiet layer of reality is not speculation. It is one of the most precisely tested and successful theories in all of science. Every modern technology, and from the devices we use every day to the deepest experiments in physics, depends on it being true. So tonight, rather than rushing toward answers, we'll slow down. We'll move gently from the familiar world of everyday experience into the deeper structure that lies beneath it. Along the way, we'll explore ideas that challenge intuition, reshape our understanding of reality, and invite us to see the universe in a completely different way, not as a collection of solid objects moving through space, but as something quieter, more subtle, and perhaps more beautiful. So, wherever you are, get comfortable, and let's begin. As we begin to explore the deeper layers of reality, it helps to start with something very familiar, not the universe itself, but the way we experience it. At first glance, the world feels stable, predictable, and reassuringly solid. A cup rests on a table. A book stays where it is placed. If something moves, it follows a path that makes sense. Cause leads to effect in a way that feels almost obvious, as though the universe is quietly following rules we instinctively understand. But this sense of clarity is not something we were born with by accident. It is something that has been shaped, slowly and carefully, over millions of years. Human perception did not evolve to reveal the true nature of reality. It evolved to help us survive. This idea is explored in a particularly striking way by cognitive scientist Donald Hoffman, through what he calls the interface theory of perception. His proposal is simple, but deeply unsettling once you sit with it. According to Hoffman, our senses do not show us the world as it truly is. Instead, they present a simplified interface, much like the icons on a computer screen. When you look at a file on your desktop, you see a small, tidy symbol. You do not see the billions of electrical signals, magnetic states, and physical processes that actually store the information. The icon is not a lie, but it is not the full truth either. It is a useful shortcut. In the same way, the objects you see around you are not necessarily how reality exists at its deepest level. They are what your brain has learned to display, because those representations are useful for navigating the world. From an evolutionary perspective, accuracy is not the goal, survival is. If a simplified, slightly distorted version of reality helps an organism avoid danger, find food and reproduce, then that version will be favoured. Over time, natural selection rewards usefulness, not truth. And so, what we experience as a clear and solid world may actually be more like a carefully designed interface, one that hides far more than it reveals. This begins to explain why certain ideas in physics feel so uncomfortable. It is not just that they are complex, it is that they do not fit the interface our minds have been trained to use. To understand this tension more clearly, it helps to look at how physics itself developed. For centuries, the dominant framework for understanding the universe was what we now call classical physics. Much of this framework was built on the work of Isaac Newton in the late 17th century. Newton's laws of motion describe how objects move under the influence of forces, and they do so with remarkable accuracy at everyday scales. If you throw a ball, its path can be predicted. If you push an object, it accelerates in a way that can be calculated. These rules are not just useful, they align beautifully with our intuition. Objects have positions, they have velocities, they follow continuous paths through space and time. Given enough information, you can, in principle, predict exactly what will happen next. This worldview feels natural because it mirrors our daily experience. It suggests a universe that is orderly, deterministic, and understandable. But even within classical physics, there were early hints that this intuitive picture might not be complete. One of the scientists who reflected deeply on this was Henri Poincaré, a French mathematician and physicist working in the late 19th and early 20th centuries. Poincaré recognized that our scientific descriptions are not direct reflections of reality, but constructions shaped by human perception and mathematical convenience. He explored how even simple systems could behave in ways that were extremely sensitive to initial conditions, a concept that would later become central to chaos theory. This meant that, in practice, perfect prediction was often impossible, even if the underlying laws were deterministic. More importantly, Poincaré emphasized that our concepts of space, time, and motion are not necessarily absolute truths. They're frameworks we use to organize experience. This insight quietly challenges the idea that our intuition is a reliable guide to the structure of the universe. And yet, despite these early warnings, the classical picture remained dominant for a long time. It worked extraordinarily well for describing planets, projectiles, machines, and nearly everything visible to the human eye. So naturally it came to feel not just useful, but fundamentally correct. The world appeared to be made of solid objects moving through a continuous space, governed by clear and predictable laws. There was no obvious reason to question this. But there was an important limitation hidden within this success. Classical physics was built from observations at a particular scale, the scale of everyday human experience, objects we can see, distances we can measure directly, times we can perceive. At these scales, the simplified interface provided by our senses aligns closely enough with reality that the classical description works. However, as scientists began to look more closely, to examine phenomena at much smaller scales, the familiar picture started to break down. The deeper they looked, the less the universe resembled the solid, predictable world of intuition. Instead of definite positions, they found uncertainty. Instead of clear paths, they found probabilities. Instead of independent objects, they found subtle connections that seemed to ignore distance altogether. At first, these discoveries were not seen as a complete overturning of the classical view. They were treated as small anomalies, details to be worked out. But gradually it became clear that something far more profound was happening. The rules that govern the microscopic world are not just slightly different from those of everyday life. They are fundamentally different, and this is where the feeling of strangeness begins to emerge. It is not that the universe is behaving irrationally. It is that our expectations, shaped by evolution and reinforced by classical physics, are no longer reliable. We are trying to understand a deeper layer of reality using tools that were never designed for it. It's a bit like trying to understand the inner workings of a computer by looking only at the icons on the screen. The interface is helpful, but it hides the complexity beneath. As we move forward, this idea will remain quietly in the background. Whenever something in quantum physics feels confusing, paradoxical, or even impossible, it is worth remembering that the discomfort may not come from the universe itself, but from the limits of the way we're used to seeing it. The world our minds were built for is not the world as it truly is, and what we are about to explore is not a different universe, but a deeper view of the same one that does not always align with intuition, but follows its own consistent and remarkably precise logic. So as we continue, there is no need to force understanding too quickly. It is enough for now to gently loosen our expectations and allow the possibility that reality may be far more subtle than it first appears. By the late 19th century, physics had reached a point of quiet confidence. The laws of motion described by Isaac Newton, combined with the theory of electromagnetism developed by James Clerk Maxwell, seemed to offer a complete and unified picture of the physical world. Planets moved in predictable orbits. Light behaved as a wave. Energy flowed in ways that could be calculated with precision. There was even a growing sense among some scientists that the major work of physics had already been done. And yet, beneath this calm surface, small inconsistencies had begun to appear. They were not immediately dramatic. They did not suggest a crisis, but they were persistent and they refused to go away. In the year 1900, the British physicist Lord Kelvin gave a lecture in which he described what he called two clouds on the horizon of physics. It is a wonderfully understated phrase. Not storms, not disasters, just clouds. The first cloud concerned the nature of light and the puzzling results of experiments attempting to detect the motion of the Earth through a medium known as the luminiferous ether. The second cloud was related to the distribution of energy in thermal radiation, something that seemed simple at first glance, but turned out to be deeply problematic. It was this second cloud that would quietly open the door to an entirely new way of understanding reality. To see why, it helps to consider a very ordinary object, something like a piece of metal heated until it glows. As the temperature of the metal increases, it begins to emit light. At first, it glows a dull red. As it becomes hotter, the colour shifts through orange, then yellow, and eventually toward white. This process is known as blackbody radiation, and it became a central focus of study in the late 19th century. The term blackbody refers to an idealized object that absorbs all incoming radiation and emits energy purely based on its temperature. While no object is a perfect blackbody, many materials approximate this behavior closely enough for careful study. Scientists such as Gustav Kirchhoff established the fundamental laws describing how such objects emit radiation. Kirchhoff showed that the spectrum of emitted light depends only on temperature, not on the specific material. This was an important step, but it did not fully explain how the energy was distributed across different wavelengths of light. Wilhelm Wien made further progress by proposing what is now known as Wien's displacement law, which relates the peak wavelength of emitted radiation to temperature. As an object becomes hotter, the peak shifts towards shorter wavelengths, which is why hotter objects appear bluer. But there was still a deeper question that remained unanswered. How exactly is the energy distributed across all wavelengths? Classical physics attempted to answer this using well-established principles. The idea was to treat the radiation inside a cavity as a collection of electromagnetic waves, each contributing to the total energy. This approach led to a formula known as the Rayleigh-Jeans law. At longer wavelengths, the predictions matched experimental results quite well. But at shorter wavelengths, something strange happened. The predicted energy did not level off or decrease. Instead, it increased without bound. According to the classical model, a heated object should emit an infinite amount of energy at very short wavelengths. This result is known as the ultraviolet catastrophe. It is a rather dramatic name, and in this case, it is entirely justified. An infinite energy output is not just incorrect. It is physically impossible. No real object behaves this way. And yet, the mathematics of classical physics led directly to this conclusion. This created a quiet but undeniable problem. The theory that had worked so well in so many situations was now producing results that clearly did not match reality. For a time, this discrepancy was treated as a technical issue, something that could be resolved with further refinement. But one physicist working in Berlin took a different approach. Max Planck was not initially trying to revolutionize physics. In fact, he was attempting to preserve it. His goal was to find a mathematical expression that would fit the observed data for blackbody radiation. After considerable effort, Planck discovered that he could match the experimental results if he made a very specific and rather unusual assumption. He proposed that energy is not emitted or absorbed continuously, but in discrete packets. These packets, which he called quanta, have an energy that depends on the frequency of the radiation. The relationship can be described in words as follows: energy equals a constant multiplied by frequency. This constant, now known as Planck's constant, has a very small value, approximately 6.63 times 10 to the minus 34 joule seconds. It is difficult to fully appreciate just how small this number is. It means that at everyday scales, the quantization of energy is so fine that it appears continuous, but at very small scales, the discreteness becomes significant. Planck introduced this idea somewhat reluctantly. He did not initially believe that energy was truly quantized in a fundamental sense. For him, it was a mathematical trick, a way to make the equations fit the data. And yet this trick worked perfectly. It resolved the ultraviolet catastrophe. It matched experimental observations across all wavelengths, and it introduced almost quietly a completely new way of thinking about energy. Instead of flowing smoothly like a continuous stream, energy appeared to come in individual units, like droplets. This was a subtle shift, but its implications were profound. For centuries, physics had been built on the assumption of continuity. Space was continuous, time was continuous, energy was continuous. Now, for the first time, there was strong evidence that at least one of these quantities might be fundamentally discrete. This marked the beginning of a deeper transformation. At first, the significance of Planck's idea was not fully recognized. It was seen as a useful adjustment, not a foundational change. But as more experiments were conducted, and as other phenomena were examined, the cracks in the classical picture began to widen. What had once seemed like a stable and complete description of reality was starting to show signs of strain. The confidence of the late 19th century gave way to a more cautious and perhaps more honest perspective. It became clear that the familiar rules of classical physics were not universal. They worked remarkably well in certain domains, but they were not the final word. And perhaps most importantly, the emerging problems were not just technical, they were conceptual. They suggested that the underlying assumptions about how the world works, about continuity, determinism, and the nature of energy, might need to be reconsidered. This is where the tone of physics begins to change. The shift is not abrupt. It does not feel like a sudden break. Instead, it is more like a slow realization that the ground beneath your feet is not quite as solid as it once seemed. The equations still work in many situations. The predictions are still accurate within familiar limits, but there is now an awareness that something deeper lies beneath, something that does not fully align with the intuitive picture. And so, the journey continues, from a world that once felt complete and predictable, into one where the rules are still precise but no longer obvious. A world where even something as simple as energy begins to behave in ways that challenge the very foundations of how we think about reality. As the idea of quantized energy began to settle into physics, another question quietly emerged. If energy comes in discrete packets, what does that mean for light itself? For much of the 19th century, light had been understood as a wave. This view was supported by a wide range of experiments, including interference and diffraction, which showed that light could spread out, overlap, and form patterns in ways that only waves were thought to do. James Clerk Maxwell's equations described light as an electromagnetic wave traveling through space, oscillating in electric and magnetic fields. These equations were elegant, predictive, and remarkably successful. So when Max Planck introduced the idea that energy might be quantized, it did not immediately imply that light itself was made of discrete units. The wave picture still seemed secure. But then, in the early years of the 20th century, a new experiment began to challenge that assumption. This experiment is known as the photoelectric effect. Imagine a clean metal surface exposed to light. According to classical wave theory, if you shine light on the metal, energy should gradually build up within the material. Given enough time, electrons should gain enough energy to escape from the surface. The brighter the light, the more energy should be delivered, and eventually electrons should be emitted. This seems straightforward. But when physicists actually performed the experiment, the results were not what classical theory predicted. First, electrons were emitted almost instantly, even when the light was very dim. There was no gradual build-up of energy. Second, increasing the brightness of the light did not increase the energy of the emitted electrons. It only increased the number of electrons. And third, and perhaps most puzzling, there was a threshold frequency. If the light was below a certain frequency, no electrons were emitted at all, no matter how intense the light was. This was deeply confusing. According to wave theory, energy should depend on intensity, not frequency. But the experiment clearly showed that frequency was the key factor. In 1905, Albert Einstein provided an explanation that built directly on Planck's idea of quantized energy. Einstein proposed that light itself is made of discrete packets, which we now call photons. Each photon carries a specific amount of energy, determined by its frequency. In words, this relationship can be expressed as energy equals Planck's constant multiplied by frequency. This means that higher frequency light, such as ultraviolet, consists of photons with more energy, while lower frequency light, such as red light, consists of photons with less energy. When a photon strikes the metal surface, it transfers its energy to a single electron. If that energy is sufficient to overcome the binding energy holding the electron in place, the electron is released. If the photon does not have enough energy, no amount of additional photons will help. Each interaction is individual, not cumulative. This explanation matched the experimental results perfectly. It explained the immediate emission of electrons, the dependence on frequency, and the independence from intensity when it comes to individual electron energy. But it came at a cost. If light is made of particles, what happens to its wave behavior? For the first time, light seemed to resist being placed into a single category. It behaved like a wave in some experiments and like a particle in others. This dual nature did not fit comfortably within the existing framework of physics. It was not simply a matter of choosing one description over the other. Both were necessary, and yet they appeared to contradict each other. This was one of the earliest signs that the categories we rely on, wave and particle, might not be fundamental features of reality but rather convenient labels that break down under closer inspection. As the 20th century progressed, this idea deepened. Physicists began to explore not just the energy and motion of particles, but also the role of information in physical systems. One of the most influential thinkers in this area was John Archibald Wheeler. Wheeler introduced a striking phrase, "it from bit." The idea behind this phrase is that every physical quantity, every particle, every field, ultimately arises from information. In this view, the fundamental building blocks of reality are not objects, but yes or no answers, bits of information. It is a radical shift in perspective. Instead of asking what something is made of, Wheeler's approach encourages us to ask what can be known about it, and how that knowledge is established. This brings us to one of the most intriguing developments in quantum physics, the role of measurement not just in determining outcomes, but in shaping them. Wheeler proposed a series of thought experiments known as delayed choice experiments. The basic idea is deceptively simple. In a typical experiment, a photon passes through a setup that allows it to behave either like a wave or like a particle, depending on how the experiment is arranged. But in a delayed choice experiment, the decision about how to measure the photon is made after the photon has already entered the system. In some versions, the choice is made so late that, in a classical sense, the photon should have already decided whether to behave as a wave or a particle, and yet the results show that the outcome still depends on the measurement. It is as though the photon does not commit to a definite behavior until the measurement is made, even if that measurement occurs after the photon has passed the point where the decision would seem to matter. This is not easily explained using classical ideas of cause and effect. It suggests that the distinction between past and future, at least at the quantum level, may not be as straightforward as it appears. These ideas have moved beyond thought experiments and into real laboratories. Physicists such as Anton Zeilinger and his research group have conducted sophisticated experiments in quantum optics, testing the foundations of quantum mechanics with remarkable precision. Zeilinger's work has explored quantum entanglement, quantum teleportation, and the role of information in physical systems. In one series of experiments, entangled photons were used to demonstrate that measurement choices made in one location could influence correlations observed in another, even when the events were separated by large distances. These experiments do not allow for faster-than-light communication, but they do reveal that quantum systems are deeply connected in ways that do not align with classical intuitions about locality and independence. What becomes increasingly clear is that light is not just a carrier of energy. It is also a carrier of information. Each photon carries not only energy, but also properties such as polarization, phase, and direction, all of which can encode information. In modern physics, this idea has become central. Quantum information theory treats physical systems as carriers of information, and processes such as measurement, entanglement, and decoherence are understood in terms of how information is created, transferred, and transformed. This does not replace the concept of energy, but it complements it. It suggests that to fully understand the behavior of light and matter, we must consider not just what is happening, but what can be known and how that knowledge is structured. And so, the simple question of what light is becomes much more subtle. It is not just a wave, it is not just a particle, it is not even just energy. It is something that carries both energy and information, behaving in ways that depend on how it is observed and measured. The categories that once seemed so clear begin to blur, and as they do, the world becomes a little less familiar, and a little more interesting. Not chaotic, not random in a careless sense, but structured in a way that does not fit neatly into the boxes we have inherited from everyday experience. It is a quiet shift, but an important one. A movement away from thinking of the universe as made of things, toward thinking of it as made of relationships, interactions, and information. And as this perspective continues to unfold, the strangeness of quantum physics begins to feel less like a flaw, and more like a hint that we're finally starting to see reality in a slightly clearer way. As the idea of light behaving both as a wave and as a particle began to settle into physics, an even more curious possibility emerged. What if this dual behavior was not limited to light? What if matter itself, the very substance of the world around us, also had a wave-like nature? This idea was proposed in 1924 by a young French physicist named Louis de Broglie. De Broglie suggested that every particle with momentum is associated with a wavelength. In simple terms, anything that moves, whether it's an electron or a grain of dust, has a wave aspect. He expressed this relationship in a form that can be described as follows: wavelength equals Planck's constant divided by momentum. Here, momentum refers to the product of mass and velocity. The larger the momentum, the shorter the wavelength. At everyday scales, this wavelength is unimaginably small. For something like a baseball, the wavelength is so tiny that it has no observable effect. This is why classical physics works so well for large objects, but for very small particles such as electrons, the wavelength becomes significant. And this was not just a theoretical idea. In the late 1920s, experiments conducted by Clinton Davison and Lester Germer at Bell Telephone Laboratories, along with similar work by George Paget Thompson, provided direct evidence that electrons can behave like waves. When electrons were fired at a crystal, they produced interference patterns, the same kind of patterns seen when light waves overlap. This was a remarkable confirmation. Particles that had always been thought of as tiny solid objects were now showing clear wave behavior. At this point, the distinction between waves and particles began to feel less like a fundamental divide, and more like a limitation of language. The question was no longer whether something is a wave or a particle, but how it can exhibit properties of both. As physicists worked to understand this, different interpretations began to take shape. One of the most intriguing alternatives to the mainstream view came from a physicist named David Bohm. Bohm developed what is now known as the pilot wave theory, also referred to as Bohmian mechanics. In this framework, particles always have definite positions and trajectories. They move through space in a well-defined way, guided by an underlying wave. This wave, often called the pilot wave, does not simply represent probability. It has a real, physical role in directing the motion of particles. In other words, the randomness observed in quantum experiments is not fundamental. It arises because we do not have access to the full information about the system. According to Bohm's theory, if we knew all the hidden variables, all the details of the system, we could, in principle, predict the exact behavior of every particle. This idea challenges one of the central conclusions of standard quantum mechanics, which treats probability as a fundamental feature of reality, not just a reflection of incomplete knowledge. Bohm's interpretation restores a sense of determinism. It suggests that beneath the apparent randomness there is a deeper level of order, a hidden structure that governs the motion of particles in a precise and predictable way. To describe this deeper level, Bohm introduced the concept of the implicate order. The implicate order refers to an underlying reality in which everything is interconnected, enfolded into a deeper whole. What we observe as separate objects and events, what Bohm called the explicate order, is simply an unfolded view of this deeper structure. It is a bit like watching waves on the surface of the ocean. The waves appear separate, each with its own shape and motion. But beneath the surface, the water is part of a continuous whole. In Bohm's view, particles are like those waves, localized expressions of a deeper, unified process. This idea is not just philosophical, it has mathematical foundations and produces predictions that align with standard quantum mechanics in many situations. However, it comes with its own challenges. One of the most significant is that Bohm's theory is explicitly non-local. This means that the behavior of a particle can depend on conditions elsewhere in the system, even at great distances. Changes in one part of the system can influence another part instantly, without any signal travelling between them in the usual sense. This feature makes many physicists uncomfortable, because it seems to conflict with the principles of relativity, which limit the speed at which information can travel. As a result, while Bohmian mechanics remains a valid and consistent interpretation, it is not the most widely accepted one. The mainstream view of quantum mechanics, often associated with the Copenhagen interpretation, takes a different approach. In this view, the wave function does not represent a physical wave guiding particles. Instead, it represents a probability distribution, a mathematical description of the likelihood of different outcomes. Particles do not have definite positions until they are measured. Before measurement, they exist in a superposition of possibilities. This interpretation embraces uncertainty as a fundamental aspect of reality. It does not attempt to restore determinism. Instead, it accepts that at the quantum level, events are inherently probabilistic. Both approaches, Bohm's deterministic model and the standard probabilistic interpretation, produce the same experimental predictions in many cases. This is what makes the situation so interesting. We have multiple ways of describing the same underlying phenomena, each with its own assumptions about what is real and what is not. This raises a deeper question. Is the randomness we observe truly fundamental? Or is it a reflection of hidden processes that we have not yet discovered? At present, there is no definitive answer. But the existence of these different interpretations suggests that our understanding is still incomplete. It also invites us to consider the possibility that what appears random on the surface may be part of a more subtle and ordered structure beneath. This idea appears in many areas of physics. In fluid dynamics, complex patterns can emerge from simple underlying rules. In chaos theory, systems that follow deterministic laws can produce behavior that looks unpredictable. And in quantum mechanics, the relationship between determinism and probability remains an open and fascinating question. What becomes clear is that the classical categories we once relied on, wave and particle, deterministic and random, are not sufficient to fully describe what is happening. They are useful approximations, but they do not capture the full picture. Instead, we are faced with a more nuanced reality, a reality in which particles can behave like waves, waves can guide particles, and underlying structures may exist beyond what we can directly observe. It is not that the universe is disordered. If anything, it may be more ordered than we realize, but in a way that is not immediately visible. The challenge is that our usual ways of thinking are not well suited to grasping this deeper level. We're used to clear categories, simple distinctions, and predictable outcomes. Quantum physics gently dissolves these boundaries. It does not replace them with chaos, but with something quieter, a kind of hidden coherence that reveals itself only through careful observation and subtle reasoning. And as we continue to explore this sense of hidden order, just beneath the surface of apparent randomness, will begin to play an increasingly important role in how we understand the nature of reality itself. If there is a single experiment that captures the strange, delicate nature of quantum reality, it is the double-slit experiment. At first glance, it appears almost simple. Imagine a barrier with two narrow openings placed between a source of particles and a screen. When particles are fired toward the barrier, they pass through the openings and strike the screen behind it. If you were to think in classical terms, the expectation is straightforward. Each particle would pass through one slit or the other, and over time, you would see two clusters forming on the screen, one aligned with each opening. That is exactly what happens if you perform this experiment with small solid objects, like grains of sand. But when the experiment is carried out with light, or even with individual particles such as electrons, something very different appears. Instead of forming two clusters, the particles create a pattern of alternating bright and dark bands on the screen. This pattern is known as an interference pattern, and it is characteristic of waves. It suggests that each particle is not simply passing through one slit or the other. Instead, it behaves as though it passes through both slits at the same time, interfering with itself. This is already unusual, but the experiment becomes even more intriguing when it is performed in a way that sends particles one at a time. You might expect that sending individual particles would eliminate any possibility of interference. After all, how can a single particle interfere with anything? And yet, even when particles are emitted one by one, the interference pattern gradually builds up over time. Each particle arrives at the screen as a single point, but the distribution of many such points forms the same wave-like pattern. It is as though each particle carries within it a spread-out set of possibilities, and each detection contributes to a larger pattern that reflects those possibilities. At this stage, it seems as though particles behave like waves while travelling, and then appear as localized points when detected. But the story does not end there. Physicists then asked a simple question. What happens if we try to observe which slit the particle goes through? To answer this, detectors can be placed near the slits to determine the path of each particle. When this is done, something remarkable happens. The interference pattern disappears. Instead of the familiar bands, the particles now form two clusters, as though they are behaving like classical particles once again. The act of measuring which path the particle takes seems to change the outcome. This is not a matter of disturbing the particle in a mechanical sense. Even carefully designed experiments that minimize disturbance still show the same effect. What matters is not the physical impact of the measurement, but the availability of information about the system. If the path information is known, or even in principle knowable, the interference pattern vanishes. If the path information is not available, the interference pattern returns. This suggests that the behavior of the particle is not determined solely by its physical properties, but also by the experimental context, by what is being measured, and what information is accessible. To explore this further, physicists developed more refined versions of the experiment. One such approach involves what are known as weak measurements. In a weak measurement, the interaction between the measuring device and the system is deliberately made very gentle. The goal is to extract some information without fully disturbing the system. Individually, these measurements provide only a small amount of information, often buried in noise. But when many such measurements are combined, patterns begin to emerge. These experiments have revealed something quite subtle. It is possible to gather partial information about the paths taken by particles, while still preserving aspects of the interference pattern. This suggests that the transition between wave-like and particle-like behavior is not an all-or-nothing process. Instead, it depends continuously on how much information is obtained. The more precisely we know the path, the less interference we see. The less we know, the more the wave-like pattern is preserved. This introduces a new way of thinking about reality. It is not simply that particles behave differently under different conditions. It is that the nature of their behavior is tied to the information available about them. This idea is taken even further in the work of Yakir Aharonov and his collaborators. Aharonov developed what is known as the time-symmetric formulation of quantum mechanics. In this framework, the state of a quantum system is influenced not only by its past, but also by its future measurements. This may sound unusual at first, but it arises naturally when considering certain quantum experiments. In some cases, the outcome of a measurement appears to depend on both the initial preparation of the system and the way it is later measured. The system is described using two wave functions, one evolving forward in time and one evolving backward. Together, they provide a more complete description of the system. This does not mean that information is literally travelling backward in time in a classical sense. Rather, it suggests that the quantum description of a system is not fully defined until both preparation and measurement are taken into account. The implications are subtle, but important. They suggest that the properties of a quantum system are not fixed in advance. Instead, they're shaped by the entire experimental arrangement, including choices made about how to measure the system. This idea is closely related to delayed choice experiments, where the decision about how to measure a particle is made after it has already entered the experimental setup. In such experiments, the outcome still depends on the measurement choice, even though that choice is made at a point where, classically speaking, it should no longer matter. Taken together, these results point toward a picture of reality that is more flexible than we might expect. Instead of having definite properties at all times, quantum systems seem to exist in a range of possibilities, with specific outcomes emerging only when interactions occur. The double-slit experiment, in all its variations, highlights this fragility. Not fragility in the sense of weakness, but in the sense of sensitivity. The outcome depends delicately on the conditions of observation. A small change in what is measured, or how it is measured, can lead to a completely different result. This does not mean that reality is unstable or arbitrary. The patterns observed in these experiments are consistent, repeatable, and described by precise mathematical laws. But it does mean that the classical idea of a fixed observer-independent reality does not fully apply at the quantum level. Instead, what we find is a reality that is, in some sense, participatory. The properties of a system are not entirely separate from the way it is observed. They emerge through interaction. This can feel unsettling at first, because it challenges the idea that the world exists in a fully defined way, independent of observation. But it can also be seen as an invitation to think more carefully about what we mean by existence in the first place. At the quantum level, existence may not be about having fixed properties at all times. It may be about the potential for different outcomes, with specific results arising when systems interact. The double-slit experiment does not give us a final answer to these questions, but it provides a clear and powerful demonstration that the categories we rely on, wave or particle, known or unknown before or after, are not as rigid as they appear. They depend on context, on measurement, and on the flow of information. And as we continue to explore these ideas, the sense of strangeness begins to take on a different quality. It is no longer just confusion. It becomes a kind of quiet recognition that the deeper structure of reality is more subtle, more interconnected, and more responsive than the simple picture we began with. A picture that does not break under observation, but gently reshapes itself in response to it. As the role of measurement becomes more difficult to ignore, a deeper question begins to take shape. What exactly is an observation? At first, it seems like a simple idea. To observe something is to look at it, to measure it, to record its properties. But in quantum physics, this familiar concept becomes more subtle. Observation is not just about seeing, it is about interaction. When a quantum system is measured, it interacts with a measuring device. This interaction changes the system in a way that cannot be ignored. It is not a passive process, it is an exchange. And this is where the idea of participation begins to emerge. One of the physicists who explored this idea most deeply was John Archibald Wheeler. Wheeler proposed what he called the participatory universe. In this view, the universe is not a fixed stage on which events simply unfold. Instead, it is something that is, in part, shaped through acts of observation. This does not mean that human consciousness creates reality in a direct or mystical sense. Wheeler was careful to avoid that interpretation. Rather, he suggested that the process of measurement, carried out by physical systems interacting with one another, plays a fundamental role in bringing definite outcomes into existence. In Wheeler's words, we are not just observers of the universe, we are participants. This idea becomes easier to approach when we think in terms of information. Every measurement can be understood as a process in which information is obtained. Before the measurement, a system may be described by a range of possible outcomes. After the measurement, one specific outcome is realized and information is gained. This shift from possibility to actuality is central to quantum mechanics. But what is the nature of the description we use before the measurement? This question leads to a modern interpretation known as quantum Bayesianism, or Cubism. Developed by physicists such as Christopher Fuchs, Cubism takes a rather different approach to understanding quantum states. In the traditional view, the wave function is often treated as a real physical entity, something that exists out there in the world, evolving according to precise mathematical laws. Cubism challenges this idea. In Cubism, the wave function is not a direct representation of physical reality. Instead, it represents an observer's knowledge, or more precisely, their expectations about the outcomes of future measurements. It is a tool for organizing beliefs about what might happen when a system is probed. This may sound abstract, but it has a clear implication. If the wave function represents knowledge, then its change during measurement is not a physical collapse in the usual sense. It is an update of information. When a measurement is made, the observer gains new information, and their description of the system changes accordingly. This is similar in some ways to updating a probability estimate when new data becomes available. For example, if you're trying to predict the weather, you might assign a certain probability to rain. When new information arrives, such as a weather report or a change in the sky, you update your expectation. The change is not happening in the weather itself at that moment, but in your knowledge of it. Cubism applies this idea to quantum mechanics, suggesting that the formalism of the theory is about managing expectations rather than describing an objective state of reality independent of observation. This perspective helps to clarify some of the puzzles associated with measurement. It shifts the focus away from trying to describe what a system really is before measurement, and toward understanding what can be known and how that knowledge changes. At the same time, it raises important questions. If the wave function represents knowledge, whose knowledge is it? And what does that imply about the nature of reality itself? Cubism answers this by emphasizing that each observer has their own perspective, their own set of expectations. But this does not mean that reality is entirely subjective. Different observers can compare their results, share information, and build a consistent picture of the world. The structure of quantum theory ensures that these shared experiences align in reliable ways. In this sense, reality is not purely objective in the classical sense, but neither is it arbitrary. It is something that emerges through consistent interactions and shared information. Returning to the idea of observation, it becomes clear that the observer in quantum mechanics does not need to be a conscious human being. Any system capable of interacting with another system and recording information can serve as an observer, a measuring device, a detector, even an environment interacting with a particle. All of these can play the role of observer. This is an important point because it keeps the discussion grounded in physics, rather than drifting into speculation about consciousness. The key idea is not awareness, but interaction. When two systems interact in a way that leaves a record, information is created, and the range of possibilities is reduced to a specific outcome. This process is often described in terms of decoherence. Decoherence occurs when a quantum system interacts with its environment in such a way that the different possible states become effectively separated, no longer able to interfere with one another. This does not require a conscious observer. It happens naturally, as systems exchange energy and information with their surroundings. As a result, the world we experience at larger scales appears stable and well-defined. The delicate superpositions that exist at the quantum level become effectively hidden, and classical behavior emerges. From this perspective, observation is not a special act performed by humans. It is a general feature of physical interactions, and yet the role of information remains central. Every interaction that leads to a definite outcome involves the creation and transfer of information. This suggests that information is not just a description of reality, but a fundamental aspect of it. The universe, in this view, is not simply made of particles and fields, but of interactions that generate and transform information. Wheeler's phrase, "it from bit," captures this idea succinctly. The it, meaning physical reality, arises from the bit, meaning information. This does not reduce everything to abstract data, but it highlights the importance of information in shaping what we observe. As these ideas come together, the picture that emerges is both subtle and coherent. Quantum systems do not carry fixed properties in isolation. Instead, their properties become defined through interactions that produce information. Observers, in the broad sense of interacting systems, participate in this process. They do not create reality from nothing, but they do play a role in bringing specific outcomes into focus. This participation is not dramatic or intrusive. It is quiet and continuous. Every interaction, every exchange of energy, every measurement contributes to the unfolding of a world that is not entirely predetermined, but not entirely random either. A world in which possibilities exist and outcomes emerge through interaction. It is a different way of thinking about reality. Not as a collection of fixed objects with predetermined properties, but as a network of relationships where information flows and structure arises from interaction. And as this perspective settles in, the role of the observer begins to feel less mysterious. Not a detached spectator, and not a creator in any mystical sense, but a participant in a universe where information, interaction, and observation are woven together in a quiet and consistent way. As the picture of quantum reality continues to unfold, one idea stands quietly at its center, not as a technical detail, but as a defining feature of how the universe behaves. This idea is known as the uncertainty principle, introduced by Werner Heisenberg in the year 1927. At first, it is often explained in a simple way. The more precisely you know the position of a particle, the less precisely you can know its momentum, and the more precisely you know its momentum, the less precisely you can know its position. But this is not just a limitation of measurement tools. It is not a matter of needing better instruments or more careful experiments. It is a fundamental property of nature itself. To understand this more deeply, it helps to consider what is meant by position and momentum. Position tells us where something is located in space. Momentum, on the other hand, tells us how it is moving. Specifically, it is the product of mass and velocity. In classical physics, there is no reason why both of these quantities cannot be known exactly at the same time. If you have precise enough measurements, you can determine both without contradiction. Quantum physics changes this picture in a very specific and mathematically precise way. The relationship can be described in words as follows. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to Planck's constant divided by 4 times p. This is not just a statement about what we know, it is a statement about what can be known. No matter how carefully an experiment is designed, no matter how advanced the technology becomes, this limit cannot be overcome. If you try to pin down a particle's position very precisely, its momentum becomes correspondingly uncertain. If you focus on momentum, position becomes less defined. It is as though the particle does not possess both properties simultaneously in a fully definite way. This leads to an important shift in perspective. Instead of thinking of particles as having exact positions and velocities at all times, quantum mechanics describes them in terms of distributions, ranges of possible values, each with an associated probability. This is not because we are missing information. It is because the concept of a perfectly defined state, in the classical sense, does not apply at this scale. The uncertainty principle is often introduced using thought experiments involving measurement disturbance, such as shining light on a particle to observe it. While these examples can be helpful, they can also be misleading if taken too literally. The deeper reason for uncertainty lies in the mathematical structure of quantum theory. Position and momentum are described by operators that do not commute. In simple terms, the order in which you apply these operations matters, and this non-commutativity leads directly to the uncertainty relationship. This may sound abstract, but it has very real consequences. It means that the world at small scales is not built from objects with perfectly defined properties, but from systems that can only be described in terms of potential outcomes. And as we move to even smaller scales, this idea becomes more pronounced. John Wheeler introduced the concept of quantum foam to describe what might be happening at the smallest possible scales of space and time. At scales on the order of the Planck length, which is approximately 1.6 times 10 to the minus 35 meters, the smooth structure of space-time predicted by general relativity is expected to break down. Instead of a continuous fabric, space-time may become turbulent and fluctuating. Tiny fluctuations in energy could cause space itself to twist, bubble, and change shape in unpredictable ways. This is not something we can observe directly with current technology. The scales involved are far beyond what our most powerful instruments can probe. But theoretical work suggests that at these scales, the very notion of a fixed background, a stable stage on which events unfold, may no longer apply. If space-time itself is subject to quantum uncertainty, then the limits of knowledge extend even deeper. It is not just that we cannot know the position of a particle precisely. It may be that the concept of position, as a fixed point in space, loses its meaning at the smallest scales. This brings us to a more relational view of reality. Carlo Rovelli, a theoretical physicist known for his work on loop quantum gravity, has developed an interpretation known as relational quantum mechanics. In this framework, properties are not absolute. They do not exist independently of observation or interaction. Instead, they exist only in relation to other systems. For example, the position of a particle is not a fixed attribute that it carries with it at all times. It is something that can be defined only relative to another system that interacts with it. This idea may seem unusual at first, but it reflects a consistent theme in quantum physics. Properties emerge through interaction. Without interaction, there is no meaningful way to assign definite values to certain quantities. This does not mean that nothing exists until it is observed. Rather, it means that the properties we use to describe systems are not intrinsic in the classical sense. They are relational. This perspective aligns naturally with the uncertainty principle. If properties are not fixed in isolation, then it is not surprising that there are limits to how precisely they can be defined simultaneously. The uncertainty is not a flaw. It is a reflection of how reality is structured. At this point, it can be helpful to step back and consider the broader picture. In classical physics, the world is made of objects with well-defined properties. These properties exist independently of observation, and they evolve in a predictable way over time. In quantum physics, the picture is different. Systems are described in terms of possibilities. Properties become defined through interaction, and there are fundamental limits to what can be known simultaneously. This does not make the theory less precise. In fact, quantum mechanics is one of the most accurate theories ever developed, with predictions confirmed to extraordinary levels of precision in experiments. But it does require a different way of thinking. Uncertainty is not a sign of incomplete knowledge waiting to be resolved. It is a feature of the world at its most fundamental level. And as we move closer to that level, toward the smaller scales of space and time, the familiar concepts of position, motion, and even space-time itself begin to soften. They do not disappear entirely, but they lose their sharp edges. What remains is a picture of reality that is less rigid, more flexible, and deeply interconnected. A picture in which certainty is replaced by possibility, and where the limits of knowledge are not barriers to understanding, but clues to the underlying structure of the universe. It is a quiet realization. Not that the world is uncertain in a chaotic sense, but that it is built in a way that does not allow for absolute precision in all things at once. And perhaps, in that gentle limitation, there is a kind of order, one that does not rely on fixed values but on relationships, interactions, and the subtle balance between what can be known and what must remain open. As the physical picture of quantum systems becomes more subtle, the language used to describe them shifts as well. In classical physics, mathematics serves as a tool for describing motion and forces. Equations track how objects move through space over time, often in ways that can be visualized quite directly. In quantum physics, the role of mathematics deepens. It no longer simply describes what we can imagine. It begins to describe structures that do not have a clear counterpart in everyday experience. One of the central developments in this shift came from Erwin Schrödinger in the year 1926. Schrödinger introduced a mathematical equation that describes how quantum systems evolve over time. At the heart of this equation is something known as the wave function. The wave function is not a wave in the ordinary sense, like a ripple on water. Instead, it is a mathematical object that encodes all the information that can be known about a system. It assigns a complex number to every possible configuration of the system, and from this, we can calculate the probability of finding the system in a particular state. In words, the key idea can be expressed as follows. The probability of finding a particle in a given state is equal to the square of the magnitude of its wave function. This rule, known as the Born rule after Max Born, connects the abstract mathematics of the wave function to observable outcomes. It allows us to move from a description of possibilities to predictions about what we will actually measure. But the wave function itself lives in a space that is not directly physical. This space is known as Hilbert space, named after the mathematician David Hilbert. Hilbert space is an abstract mathematical structure that can have many dimensions, often infinitely many. Each point in this space represents a possible state of the system. For a single particle moving in one dimension, the wave function can be visualized as a function over position. But for more complex systems, the dimensionality increases rapidly. For example, a system of two particles does not simply have twice the complexity. Instead, its wave function exists in a space that combines all possible configurations of both particles. As more particles are added, the dimensionality grows exponentially. This makes Hilbert space a very different kind of arena compared to the three-dimensional space we're used to. It is not something we can easily picture, but it is where the full description of quantum systems resides. This shift from physical space to abstract space is one of the reasons quantum mechanics feels so unfamiliar. The theory is not just describing objects moving around in space, it is describing how possibilities evolve within a mathematical structure. And yet, despite this abstraction, the predictions it produces are extraordinarily precise. Physicists such as Paul Dirac embrace this abstract approach. Dirac was known for his belief that mathematical beauty is a reliable guide to physical truth. He often followed elegant mathematical structures even when their physical interpretation was not immediately clear. This approach led him to some remarkable discoveries. One of the most famous is the prediction of antimatter. Dirac's equations for the electron suggested the existence of particles with the same mass but opposite charge. At the time, this idea seemed unusual, but a few years later, the positron was experimentally discovered, confirming Dirac's prediction. This is a powerful example of how mathematics in quantum theory is not just descriptive, but generative. It does not simply summarize what we observe, it can lead us to new phenomena that were not previously imagined. At the core of this mathematical framework is the concept of probability amplitudes. In classical probability, we assign numbers between 0 and 1 to represent the likelihood of different outcomes. These probabilities add in a straightforward way. If there are two possible paths, the total probability is the sum of the probabilities for each path. In quantum mechanics, the situation is different. Instead of probabilities, we work with probability amplitudes, which are complex numbers. These amplitudes can interfere with one another, much like waves. When two amplitudes combine, they can reinforce each other, leading to a higher probability, or they can cancel each other out, leading to a lower probability. Only after combining the amplitudes do we take the square of their magnitude to obtain a probability. This means that the structure of quantum theory allows for interference between possibilities. It is not just that multiple outcomes are possible, it is that the possibilities themselves interact. This is what gives rise to the interference patterns seen in experiments such as the double slit. Each possible path contributes an amplitude, and the combination of these amplitudes determines the final distribution of outcomes. This idea can feel quite abstract, but it has a clear physical impact. It means that the behavior of a system depends not only on what happens, but on all the ways it could happen. In some sense, the system explores many possibilities at once, and the final outcome reflects the interplay between them. This leads to a deeper question. Is mathematics simply a tool we use to describe reality, or is it something more fundamental? Some physicists and philosophers have suggested that the mathematical structure of quantum theory is not just a representation, but a reflection of the underlying nature of reality itself. In this view, the universe is not merely described by mathematics. It is, in some sense, made of mathematical relationships. Others take a more cautious approach, seeing mathematics as an extraordinarily effective language, but not necessarily the substance of reality. Either way, the success of quantum mechanics suggests that the mathematical framework captures something essential. It allows us to predict the outcomes of experiments with remarkable accuracy, often to many decimal places. For example, calculations in quantum electrodynamics, the theory that describes the interaction between light and matter, have been confirmed to an accuracy of better than 1 part in a trillion. This level of precision is difficult to achieve in any scientific field, and it speaks to the power of the underlying mathematics. And yet, despite this precision, the interpretation of the mathematics remains open to discussion. The equations tell us how to calculate probabilities, how systems evolve, and how measurements relate to outcomes. But they do not tell us, in a straightforward way, what is really happening between measurements. This is where the sense of mystery persists. The mathematics works perfectly, the predictions match experiments, but the underlying picture of reality is less clear. What we have is a framework that describes possibilities, relationships, and outcomes, without necessarily providing a simple visual model. And perhaps that is part of the lesson. At the deepest level, reality may not be something that can be fully captured by familiar images or everyday concepts. It may be something that is best understood through patterns, structures, and relationships. Expressed in the language of mathematics, this does not make it less real. If anything, it suggests that the world is more subtle than we might expect, not built from solid objects alone, but from a web of possibilities that unfold according to precise and elegant rules. Rules that we can write down, calculate, and test, even if we cannot always picture them in the way we're used to. And in that quiet space between calculation and intuition, the nature of quantum reality continues to reveal itself. Not as something chaotic, but as something deeply structured, guided by a mathematics that is both abstract and profoundly connected to the world we observe. One of the most distinctive ideas in quantum physics is the concept of superposition. At its core, superposition describes a situation in which a system exists in multiple, possible states at once, rather than occupying a single definite state. This is not simply a matter of uncertainty in the usual sense. It is not that the system has a definite state that we do not yet know. Instead, the theory suggests that before measurement, the system genuinely occupies a combination of possibilities. To make this more concrete, it is helpful to begin with a simple example. Consider a quantum system such as an electron with a property known as spin. When measured along a particular direction, the electron's spin can be found in one of two possible states, often described as up or down. In classical thinking, we might assume that the electron is always either up or down, and that measurement simply reveals which one it is. Quantum mechanics offers a different picture. Before measurement, the electron can exist in a superposition of both states. This means that it is not exclusively up or down, but in a state that includes both possibilities. When a measurement is made, the superposition appears to resolve into one of the definite outcomes. This transition from multiple possibilities to a single result is often referred to as the collapse of the wave function. The idea becomes more vivid when we consider a well-known thought experiment proposed by Erwin Schrödinger. In this thought experiment, a cat is placed in a sealed box along with a quantum system that has a 50% chance of triggering a mechanism that would be fatal to the cat. According to the principles of quantum mechanics, the system evolves into a superposition of both outcomes. As a result, before the box is opened, the cat is described as being in a superposition of alive and not alive. This is of course not meant to suggest that real cats exist in such states in any practical sense. Schrödinger introduced the scenario to highlight the apparent tension between quantum theory and everyday experience. It raises a natural question. If superposition is a fundamental feature of quantum systems, why do we not observe it at larger scales? Why do objects in our daily lives appear to have definite properties? This question leads us to the boundary between the quantum and classical worlds. In recent years, physicists have made significant progress in exploring this boundary experimentally. Advances in technology have allowed researchers to create and study superpositions in increasingly large and complex systems. For example, experiments with superconducting circuits, often referred to as quantum bits or qubits, have demonstrated superposition in systems containing billions of electrons. These circuits, used in quantum computing research at institutions such as the University of California and companies like Google and IBM, can exist in superpositions of different electrical states. Similarly, experiments with ultra-cold atoms and molecules have shown interference effects in systems much larger than individual particles. In one notable set of experiments, molecules consisting of several hundred atoms were passed through setups analogous to the double-slit experiment, producing interference patterns that confirm their wave-like behavior. These results suggest that superposition is not limited to the smallest particles. It can, in principle, extend to larger systems. However, there is a practical limitation. As systems become larger and interact more strongly with their environment, maintaining a coherent superposition becomes increasingly difficult. This process, known as decoherence, causes the different components of the superposition to lose their ability to interfere with one another. The system begins to behave in a way that appears classical. This provides one explanation for why we do not see superpositions in everyday objects. It is not that the rules change at larger scales, but that the effects become hidden due to interactions with the environment. Even so, some physicists have proposed that there may be an additional mechanism at work. One of the most prominent proposals comes from Roger Penrose. Penrose has suggested that gravity itself may play a role in causing the collapse of quantum superpositions. In his objective collapse theory, the idea is that when a system becomes sufficiently large or massive, the superposition becomes unstable due to gravitational effects. The different possible states of the system correspond to different configurations of space-time geometry. At some point, this difference becomes too great to sustain, and the system spontaneously collapses into one of the possible states. This collapse is not triggered by observational measurement. It is an intrinsic physical process. Penrose's proposal is still under investigation, and experimental tests are ongoing. Some experiments aim to place increasingly massive objects into superposition, looking for deviations from standard quantum predictions that might indicate such a collapse mechanism. These experiments are extremely challenging, requiring precise isolation from environmental disturbances and careful control of quantum states. But they represent an important effort to probe the limits of quantum theory. As we consider these ideas, the boundary between quantum and classical behavior begins to take on a new character. It is not a sharp dividing line, but a gradual transition. At small scales, superposition is clear and dominant. At larger scales, interactions with the environment and possibly intrinsic mechanisms lead to the emergence of definite outcomes. This suggests that the classical world we experience may not be fundamental. Instead, it may be an emergent phenomenon, a stable pattern that arises from the underlying quantum behavior. In this view, classical reality is not a separate layer with its own rules. It is a consequence of the quantum world, shaped by decoherence, interaction, and possibly additional processes. The stability of everyday objects, their definite positions and properties, may be the result of a kind of equilibrium, a balance between the tendency of quantum systems to explore multiple possibilities and the forces that constrain those possibilities into a single outcome. This perspective offers a way to understand why the world appears the way it does, without abandoning the principles of quantum mechanics. It also highlights the idea that what we perceive as solid and definite may be less fundamental than it seems. Beneath the surface, there may always be a range of possibilities, quietly present but no longer visible. Superposition, in this sense, is not just a technical feature of quantum theory. It is a window into a deeper layer of reality, a layer where the familiar distinction between one thing and another becomes less rigid, and where the world is not fully decided until interactions take place. This does not make reality unstable in a chaotic sense. The outcomes we observe are consistent and reliable. The patterns are well defined. The laws are precise. But it does suggest that the definiteness we experience is not the starting point. It is the result of a process in which possibilities are narrowed, interactions occur, and one outcome becomes part of the unfolding history of the universe. And as we reflect on this, the idea of superposition begins to feel less like a paradox and more like a natural extension of the principles we have already encountered. A reminder that at its deepest level, reality is not limited to a single path, but contains within it a quiet richness of possibilities waiting to be resolved. As the idea of quantization first appeared in the study of energy, it might have seemed like a small adjustment, a mathematical convenience that helped resolve a specific problem. But over time it became clear that quantization was not a minor detail. It was a defining feature of how the microscopic world is structured. One of the earliest and most important places where this becomes visible is in the structure of atoms. Atoms are not continuous blobs of matter. They have a very specific internal arrangement, with electrons bound to a central nucleus. In classical physics, one might expect electrons to orbit the nucleus in a wide range of possible paths, much like planets orbit a star. But this picture leads to a problem. An accelerating charge, such as an electron moving in a curved path, should emit electromagnetic radiation. As it loses energy, it should spiral inward and eventually collapse into the nucleus. Clearly, this does not happen. Atoms are stable. The solution came through the idea that electrons can only occupy certain discrete energy levels. This was first proposed in a simplified form by Niels Bohr in the early 20th century, and later refined through the full framework of quantum mechanics. In this picture, electrons are not free to have any energy they like. Instead, they are restricted to specific allowed values. When an electron moves from one energy level to another, it does so by absorbing or emitting a photon with an energy equal to the difference between those levels. This can be expressed in words as, the energy of the emitted or absorbed photon equals the difference between two allowed energy levels. These discrete transitions give rise to the characteristic spectral lines observed in atoms, such as the hydrogen spectrum. Each element produces a unique set of lines, acting almost like a fingerprint. This is one of the clearest pieces of evidence that energy, at least at the atomic scale, is not continuous. It comes in steps. And this idea of stepping, of discreteness, does not seem to stop at energy. As physicists began to explore deeper questions, they started to ask whether space and time themselves might also be quantized. In classical physics, space and time are treated as continuous. You can divide a distance into smaller and smaller segments without limit. You can imagine slicing time into ever shorter intervals. There is no smallest unit. But when quantum theory is combined with gravity, this picture begins to change. One approach to this problem is known as loop quantum gravity, developed by physicists including Carlo Rovelli and Lee Smolin. Loop quantum gravity attempts to describe the structure of spacetime itself in quantum terms. In this framework, space is not smooth and continuous at all scales. Instead, it is made up of tiny, discrete units, often described as loops or networks. These structures are sometimes referred to as spin networks. Each node and connection in the network represents a quantized chunk of space, with specific values for properties such as area and volume. This suggests that there is a smallest possible unit of space, below which the concept of distance loses its meaning. This scale is known as the Planck length, approximately 1.6 times 10 to the minus 35 meters. To give a sense of how small this is, if you were to take a proton, which itself is already incredibly small, and divide its diameter into 10 to the 20 parts, each part would still be vastly larger than the Planck length. At this scale, the familiar notion of smooth geometry begins to break down. Space may no longer behave like a continuous backdrop. Instead, it may have a granular structure, composed of discrete building blocks. Time, too, may have a smallest meaningful unit, known as the Planck time, which is approximately 5.4 times 10 to the minus 44 seconds. Below this scale, the distinction between before and after may not be well defined. These ideas lead naturally to the suggestion that the universe might be, in some sense, pixelated. It is an appealing analogy. Just as a digital image is made up of individual pixels, each representing a small unit of colour, space-time might be composed of fundamental units that define its structure. But this analogy should be used carefully. Unlike the pixels on a screen, which exist within a larger continuous space, the discrete units in loop quantum gravity would not sit inside a background. They would be the background. There would be no underlying smooth space beneath them. This is an important distinction. It suggests that space is not something that exists independently of the objects within it. Instead, it may be something that emerges from the relationships between these fundamental units. In this view, geometry itself becomes dynamic and relational. Distances, areas, and volumes are not fixed properties of a pre-existing space, but quantities that arise from the connections within the network. This is a significant shift from the classical picture. It aligns with the broader theme that properties in quantum physics often depend on interactions and relationships, rather than existing independently. At the same time, it raises challenging questions. How do these discrete structures give rise to the smooth space-time we experience at larger scales? How do the familiar laws of general relativity emerge from this underlying network? These are active areas of research, and many details remain unresolved. But the idea that quantization might extend beyond energy to include space and time themselves is a powerful one. It suggests that the discreteness first observed in atomic systems may be a reflection of a deeper principle, a principle that shapes not only the behavior of particles, but the very fabric of the universe. As we consider this possibility, the notion of a continuous, infinitely divisible world begins to soften. In its place, we find a picture of reality that is built from fundamental units, connected in intricate ways, not rigid or mechanical but structured and precise. And while this structure may be far removed from everyday experience, it is not arbitrary. It is governed by mathematical rules, tested through theoretical consistency, and, where possible, experimental hints. Quantization, in this broader sense, becomes more than a feature of specific systems. It becomes a guiding idea, a suggestion that at the deepest level, reality may be composed not of smooth continua, but of discrete elements, woven together to form the world we observe. And in that quiet shift, from continuity to discreteness, another layer of the universe reveals itself. Not as something fragmented or broken, but as something finely structured, built from the smallest possible pieces, arranged in ways that give rise to everything we see. As quantum ideas continued to unfold, one phenomenon began to stand out as particularly difficult to reconcile with classical thinking. This phenomenon is known as entanglement. At first, it can be described in a relatively simple way. When two particles become entangled, their properties are linked in such a way that measuring one immediately provides information about the other, no matter how far apart they are. But this description, while accurate, does not fully capture what is happening. Entanglement is not just a strong correlation, like two coins that always land on opposite sides. In a classical system, correlations arise from shared history or common causes. Once the coins are separated, nothing new happens between them. In quantum entanglement, the situation is more subtle. The particles do not carry predetermined values that are simply revealed upon measurement. Instead, the outcomes themselves are not fixed until the measurement occurs, and yet they are still linked in a precise way. This distinction becomes clearer when we look at a famous thought experiment proposed in 1935 by Albert Einstein, Boris Podolsky, and Nathan Rosen. This is known as the Einstein-Podolsky-Rosen paradox, or a PR paradox. The goal of this thought experiment was to show that quantum mechanics might be incomplete. Einstein and his colleagues considered a pair of particles that interact and then move apart. According to quantum theory, these particles can be described by a single shared wave function, meaning their properties are entangled. If you measure a property of one particle, such as its position or momentum, you can immediately know the corresponding property of the other particle. Einstein found this deeply troubling. He believed that physical properties should exist independently of measurement, and that information should not travel faster than the speed of light. The idea that measuring one particle could instantly affect another, distant particle, led him to describe the phenomenon as spooky action at a distance. To resolve this, Einstein suggested that there might be hidden variables, additional information carried by the particles that determine the outcomes in advance. In this view, the apparent connection between the particles would be explained by shared hidden properties, not by any instantaneous influence. For many years, this remained a philosophical debate, but in the 1960s, physicist John Bell developed a way to test these ideas experimentally. Bell derived inequalities that any local hidden variable theory must satisfy. Quantum mechanics, however, predicts violations of these inequalities under certain conditions. Experiments conducted over the following decades, including those by Alana Speck in the 1980s, and more recent tests with increasingly sophisticated setups, have consistently supported the predictions of quantum mechanics. These experiments show that the correlations between entangled particles cannot be explained by local hidden variables. This does not mean that information is being transmitted faster than light, in a way that could be used for communication. The outcomes are still fundamentally random, but it does mean that the classical idea of independent localized objects is not sufficient to describe what is happening. Entangled systems must be treated as a single, unified whole, even when the parts are separated by large distances. This realization has led to a shift in how entanglement is understood. Rather than seeing it as a strange and isolated phenomenon, physicists have begun to explore the possibility that entanglement is a fundamental feature of the structure of reality. One of the most intriguing developments in this direction is the idea known as ER equals EPR. This conjecture was proposed by Juan Maldacena and Leonard Susskind. The name itself reflects a connection between two seemingly unrelated concepts. EPR refers to the Einstein-Podolsky-Rosen paradox, which involves entangled particles. ER refers to Einstein-Rosen bridges, more commonly known as wormholes, which are solutions in general relativity that connect distant regions of spacetime. The conjecture suggests that these two ideas may be deeply related. In simple terms, it proposes that entangled particles might be connected by extremely tiny, non-traversable wormholes. These connections would not allow for travel or communication, but they would provide a geometric way of understanding entanglement. This is still a speculative idea, but it has gained attention because it offers a way to link quantum mechanics with the geometry of spacetime. It suggests that entanglement is not just a feature of particles, but a building block of space itself. In this view, the structure of spacetime may emerge from patterns of entanglement. Distances and connections between points in space could be determined by how strongly different parts of the system are entangled. Regions that are highly entangled might be closer in a fundamental sense, even if they appear far apart in classical terms. This idea has been explored in the context of quantum gravity and holographic theories, where the geometry of space is related to the information content of a system. While many details remain to be worked out, the general direction is clear. Entanglement is being reinterpreted not as a mysterious anomaly, but as a central organizing principle. It is a way in which different parts of a system are linked together, forming a coherent whole. This perspective helps to reduce the sense of strangeness. Instead of asking how two distant particles can influence each other, we begin to see that they are not truly separate to begin with. They are part of a single quantum system, described by a shared state. The apparent separation is a feature of our classical description, not a fundamental property of the system. This does not mean that space and distance are illusions, but it does suggest that they may not be as fundamental as they appear. They may emerge from deeper relationships that are encoded in entanglement. As this idea settles in, the nature of reality begins to shift once again. The focus moves away from individual objects and toward connections. What matters is not just what things are, but how they are related. Entanglement becomes a kind of glue, not a physical substance, but a pattern of relationships that bind systems together. And while this glue does not behave in ways that align with classical intuition, it is not arbitrary. It follows precise mathematical rules, and its effects have been confirmed through careful experimentation. In this light, the phrase "spooky action at a distance" begins to feel less like a problem and more like a reflection of a deeper truth. A truth in which separation is not absolute, and where the fabric of reality is woven from connections that extend beyond the limits of space as we usually understand it. It is a quiet but profound shift, from a world made of separate parts interacting across space, to a world in which the connections themselves are fundamental, and where what appears distant may, at a deeper level, be intimately linked. And in that shift, entanglement becomes not just a curious feature of quantum theory, but a window into the underlying structure of the universe itself. As ideas about information and entanglement began to deepen, another unexpected connection emerged, one that links gravity, geometry, and the limits of information in a surprisingly elegant way. This connection begins with the study of black holes. At first, black holes were understood primarily through the lens of general relativity, as regions of space-time where gravity becomes so strong that nothing, not even light, can escape. They were described in terms of mass, charge, and angular momentum, with a boundary known as the event horizon marking the point of no return. But in the 1970s, a new perspective began to take shape. Jacob Bekenstein proposed that black holes should have an entropy, a measure of the number of microscopic configurations consistent with their macroscopic properties. This idea was initially controversial. Entropy is usually associated with systems that have internal structure, like gases or liquids. A black hole, by contrast, seemed to be defined only by a few simple parameters. But Bekenstein noticed something intriguing. The entropy of a black hole appeared to be proportional not to its volume, but to the area of its event horizon. Shortly afterward, Stephen Hawking provided further insight by showing that black holes are not completely black. Through quantum effects near the event horizon, black holes can emit radiation, now known as Hawking radiation. This result confirmed that black holes have a temperature and therefore a well-defined entropy. The relationship between entropy and area can be expressed in words as follows. The entropy of a black hole is proportional to the area of its event horizon divided by the Planck area. The Planck area is an extremely small unit, derived from fundamental constants, and sets the scale at which quantum gravitational effects become significant. What is remarkable about this relationship is that it suggests a limit on how much information can be stored within a given region of space. Instead of scaling with volume, as one might expect, the maximum entropy scales with surface area. This led to a profound idea. If the amount of information in a region is determined by its boundary, then perhaps the description of the entire region can be encoded on that boundary. This is the essence of the holographic principle, developed by Gerard 't Hooft, and later refined by Leonard Susskind. The term holographic comes from holograms, which are two-dimensional surfaces that encode three-dimensional images. In a similar way, the holographic principle suggests that the physics within a volume of space can be fully described by information stored on its boundary. This is not just a metaphor. In certain theoretical frameworks, this idea can be made precise. One of the most important examples is the anti-de and conformal field theory correspondence, commonly known as ADS-CFT. This correspondence was proposed by Juan Maldacena in the late 1990s. It describes a relationship between two very different kinds of theories. On one side, there is a theory of gravity defined in a higher dimensional spacetime, known as anti-de Sitter space. On the other side, there is a quantum field theory without gravity, defined on the lower dimensional boundary of that space. The remarkable claim of ADS-CFT is that these two theories are equivalent. Every physical process in the higher dimensional gravitational theory has a corresponding description in the lower dimensional non-gravitational theory. This means that a universe with gravity can, in principle, be fully described by a theory that lives on its boundary. It is a striking and somewhat counterintuitive result. It suggests that the familiar three-dimensional world may not be the most fundamental description of reality. Instead, it may emerge from a more basic layer of information encoded on a lower dimensional surface. While our universe is not exactly described by anti-de Sitter space, the ideas behind this correspondence have influenced a wide range of research. They provide a framework for understanding how geometry and information might be connected at a deep level. One way to think about this connection is through the idea that space-time geometry is shaped by patterns of entanglement. In certain models, the distance between points in space can be related to how strongly the corresponding regions are entangled. Stronger entanglement corresponds to closer connections, while weaker entanglement corresponds to greater separation. This suggests that geometry itself may arise from the structure of quantum information. Space is not simply a backdrop in which things happen. It may be a consequence of how information is organized. This idea aligns with a broader theme that has been emerging. Properties, positions, and even distances are not necessarily fundamental. They may be derived from deeper relationships. In this context, information is not just something we use to describe systems. It becomes a key ingredient in the construction of reality. The holographic principle also provides insight into one of the most puzzling problems in physics, known as the black hole information paradox. If information falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what happens to that information? Does it disappear, violating the principles of quantum mechanics, or is it somehow preserved? The holographic perspective suggests that the information is not lost. Instead, it may be encoded on the event horizon and gradually released through the irradiation process, though the exact mechanism remains an area of active research. This ongoing investigation highlights the importance of understanding how information is stored, transformed, and preserved in physical systems. As these ideas come together, the picture that emerges is both subtle and compelling. Reality may not be built from objects in space in the way we once imagined. Instead, it may be constructed from patterns of information, with geometry arising as a secondary feature. The familiar three-dimensional world could be an emergent description, much like the image produced by a hologram. This does not mean that our experience of space is an illusion in a dismissive sense. It is real and consistent, shaped by the underlying structure, but it may not be the most fundamental layer. Beneath it, there may be a more abstract framework in which information, rather than matter or space, plays the central role. And in that framework, the boundaries between physics, geometry, and information begin to blur. They become different aspects of the same underlying reality, a reality that is not only governed by laws but encoded in a way that reflects deep and elegant connections between seemingly separate ideas, connections that continue to reveal themselves, slowly and quietly, as we look more closely at the structure of the universe. Time feels like one of the most certain aspects of experience. Moments pass, events unfold. The past feels fixed, the future open, and the present seems to move steadily forward, one instant at a time. This sense of flow is so familiar that it is rarely questioned. And yet, when physics looks closely at the foundations of reality, time begins to lose its simplicity. In classical physics, time is treated as a universal parameter. It flows uniformly, the same for all observers, providing a steady background against which motion and change can be measured. Even in Albert Einstein's theory of relativity, where time can stretch and contract depending on motion and gravity, it remains a central component of the description. But in certain approaches to quantum gravity, time begins to fade from the fundamental equations. One of the most striking proposals in this direction comes from Julian Barbour. Barbour has argued that time, as we experience it, may not be a fundamental feature of the universe at all. Instead, he suggests that reality consists of a collection of possible configurations, each representing a complete state of the universe. These configurations exist timelessly. There is no underlying clock that causes one configuration to evolve into another. Instead, what we perceive as the passage of time is a reflection of how these configurations are related to one another. Barbour refers to these configurations as nows. Each now is a complete snapshot of the universe, containing within it records of what we interpret as the past. For example, a particular configuration might include memories, physical traces, and structures that suggest a history. From within that configuration, it feels as though events have unfolded over time. But according to this view, the sense of flow arises from the relationships between these static configurations, not from an actual movement through time. This is a subtle but profound shift. It suggests that time may not be something that exists independently, but something that emerges from the structure of the universe. A different but related perspective comes from Carlo Rovelli, who has explored the nature of time in the context of quantum gravity. Rovelli has proposed what is known as the thermal time hypothesis. In this framework, time is not a fundamental variable built into the laws of physics. Instead, it emerges from the statistical state of a system. The idea is that time can be defined in terms of how systems evolve toward equilibrium, as described by thermodynamics. In other words, time is linked to change, and change is linked to the distribution of energy and information within a system. This connects the concept of time to entropy, which measures the number of possible microscopic configurations corresponding to a macroscopic state. As entropy increases, systems evolve in a way that gives rise to a direction, what we experience as the arrow of time. But this direction is not imposed by a universal clock. It arises from the internal structure of the system itself. This perspective helps explain why time seems to have a direction, even though the fundamental laws of physics are often symmetric with respect to time. At the microscopic level, many physical processes can run equally well forward or backward. Yet at the macroscopic level, we observe a clear progression from past to future. The thermal time hypothesis suggests that this asymmetry is not built into the basic laws, but emerges from the conditions of the system. As these ideas develop, the role of time in quantum theory becomes increasingly subtle. In standard quantum mechanics, time is often treated as an external parameter. The wave function evolves according to Schrödinger's equation, which describes how the system changes over time. But in attempts to unify quantum mechanics with general relativity, this approach encounters difficulties. In general relativity, time is not an external parameter. It is part of the dynamical structure of space-time influenced by matter and energy. When these two frameworks are combined, the resulting equations, such as the Wheeler-DeWitt equation, often do not include time in the usual sense. Instead, they describe a timeless state of the universe. This raises a challenging question. If the fundamental description of the universe does not include time, where does our experience of time come from? One possible answer is that time emerges from correlations between different parts of a system. Instead of a single, universal clock, there are relationships between variables that allow one part of the system to be used as a reference for another. For example, the position of a clock's hands can be used to describe the evolution of another system. In this sense, time is not an independent entity, but a way of describing change relative to something else. This relational view aligns with the broader themes we have encountered. Just as properties may exist only in relation to interactions, time may exist only in relation to change. There is no need for a global, absolute time that applies everywhere in the same way. Instead, there are local, context-dependent descriptions of how systems evolve. This idea may feel abstract, but it has practical implications. In quantum experiments, especially those involving entanglement and relativistic effects, there is no single, universally agreed upon order of events. Different observers may disagree on the sequence of measurements, depending on their relative motion. And yet the predictions of quantum mechanics remain consistent. This suggests that the theory does not rely on a fixed temporal order in the way classical physics does. As we reflect on these ideas, the familiar sense of time as a flowing river begins to soften. It may still be a useful and meaningful description at the level of everyday experience, but it may not be fundamental. Instead, time could be an emergent feature, a way of organizing the relationships between different parts of the universe, a way of describing change rather than a substance or dimension that exists on its own. This does not make time any less real in a practical sense. Our experiences, memories, and expectations are all structured by it. But it does suggest that the underlying reality may be more subtle, a reality in which the distinction between past, present, and future is not built into the fabric of the universe, but arises from how we interact with it. And in that quiet shift, time becomes less like a flowing current, and more like a pattern that emerges from change, from relationships, and from the way information is distributed across the system. A pattern that feels continuous and familiar, even if, at its deepest level, it is something entirely different. As quantum theory developed, it became clear that the mathematics was remarkably successful, yet the interpretation of that mathematics remained open to debate. Different ways of understanding the same equations began to emerge, each offering a slightly different picture of what reality might be doing beneath the surface. One of the most intriguing of these interpretations was proposed in 1957 by Hugh Everett III. Everett introduced what is now known as the many worlds interpretation. His idea begins with a simple observation. The equations of quantum mechanics, particularly the Schrödinger equation, describe a smooth and continuous evolution of the wave function. There is no explicit mechanism within the equation that causes a sudden collapse into a single outcome. And yet, when we perform a measurement, we observe a definite result. Everett suggested that perhaps this apparent collapse does not actually occur. Instead, all possible outcomes described by the wave function continue to exist, but they do so in separate, non-interacting branches of reality. When a measurement takes place, the system and the observer become entangled, and the combined system evolves into a superposition of different outcomes. Each outcome corresponds to a different branch, and in each branch, a version of the observer perceives a specific result. From within any one branch, it appears as though a single outcome has occurred. But from the perspective of the full wave function, all outcomes are realized. This interpretation removes the need for a special collapse process. The evolution of the system remains entirely governed by the Schrödinger equation. It is a bold idea, and it has a certain simplicity. Nothing extra needs to be added to the theory. The mathematics is taken at face value. But it also introduces a picture of reality that is far from intuitive. Instead of a single unfolding universe, there is a vast collection of branching possibilities, each representing a different version of events. Every quantum interaction, no matter how small, contributes to this branching structure. At first, this can feel overwhelming. The number of branches grows extremely rapidly, and most of them are inaccessible to us. We experience only one branch, the one in which our particular sequence of observations occurs. Despite this, the theory remains consistent with all known experimental results. One of the key mechanisms that makes this interpretation viable is decoherence. Decoherence describes how interactions with the environment cause different components of a superposition to lose coherence with one another. In practical terms, this means that once branches form, they no longer interfere. They become effectively independent. This explains why we do not observe superpositions at the macroscopic level. The environment constantly interacts with systems, causing decoherence to occur very quickly. As a result, the different branches evolve separately, and each appears classical within its own context. David Deutsch, a physicist known for his work in quantum computation, has been one of the strongest advocates for the many worlds interpretation. Deutsch has argued that this interpretation provides a natural framework for understanding quantum computation. In a quantum computer, superpositions allow the system to explore multiple computational paths simultaneously. Deutsch suggested that this can be understood as computations taking place across multiple branches of the multiverse. While this is an interpretation rather than a direct physical statement, it highlights how the many worlds perspective can offer intuitive ways of thinking about quantum processes. At the same time, not all physicists are comfortable with this view. The idea of an enormous number of parallel realities raises questions about testability and simplicity. If all possible outcomes occur, how do we make sense of probability? Why do we observe specific frequencies of outcomes, rather than all possibilities equally? Various approaches have been developed to address these questions, including attempts to derive the Born rule from decision theory and rational reasoning. These efforts show that even within the many worlds framework there are still open questions. In contrast, collapse-based interpretations take a different approach. In these interpretations, the wave function does not continue to evolve indefinitely in a superposition of outcomes. Instead, it undergoes a real physical collapse when a measurement occurs. This collapse selects one outcome from the range of possibilities. The Copenhagen interpretation, associated with Niels Bohr and Werner Heisenberg, is one of the earliest examples of this approach. In this view, the wave function provides probabilities for different outcomes, and measurement causes one of those outcomes to be realized. However, the exact mechanism of collapse is not specified in detail. Other collapse models, such as those proposed by Girardi, Rimini, and Weber, introduce explicit mechanisms for collapse, often involving spontaneous localization events. These models aim to provide a more complete description of how definite outcomes arise. Each of these interpretations has its strengths and challenges. The many worlds interpretation offers a mathematically clean and continuous evolution, but at the cost of introducing a vast multiplicity of realities. Collapse-based interpretations preserve a single outcome, but require additional mechanisms that are not present in the standard equations. Importantly, both approaches make the same experimental predictions in most situations. This means that, at present, there is no definitive experimental way to distinguish between them. As a result, the choice between interpretations often comes down to philosophical preferences about simplicity, realism, and the nature of explanation. This situation highlights an important aspect of quantum theory. The mathematics is precise and well tested, but the meaning of that mathematics is not uniquely determined. Different interpretations can coexist, each offering a different way of understanding the same underlying structure. This does not indicate a flaw in the theory. Rather, it reflects the fact that our conceptual frameworks are still adapting to a domain that does not align with everyday intuition. As we consider these different perspectives, it becomes clear that the question is not simply which interpretation is correct. It is also about what kind of picture of reality we find most coherent and satisfying. Is reality fundamentally deterministic, with all possibilities unfolding in parallel? Or is there a genuine randomness, with outcomes selected through a collapse process? Or perhaps there is a deeper framework that we have not yet fully discovered, one that unifies these perspectives in a more complete way. For now, the answer remains open, and in that openness there is a certain quiet freedom, a recognition that our understanding is still evolving, and that the nature of reality may be richer than any single interpretation can capture. The many worlds interpretation, along with its alternatives, serves as a reminder that quantum physics does not just challenge our expectations about how the world behaves, it also challenges our ideas about what it means for something to exist. And as we continue to explore these ideas, the boundaries between possibility and reality begin to blur, not in a chaotic way, but in a way that invites deeper reflection on the structure of the universe and our place within it. As the role of information becomes more central in quantum theory, a quiet shift begins to take place. Instead of asking what the universe is made of, some physicists have started asking a different question. What is the universe doing? And more specifically, is it processing information? This idea builds on the earlier insight from John Archibald Wheeler, who suggested that physical reality arises from information. His phrase, "it from bit," pointing toward a universe where yes or no questions form the foundation of everything. At first, this may seem like a philosophical suggestion, but over time, it has developed into a more concrete framework. One of the physicists who has explored this idea in detail is Seth Lloyd. Lloyd has proposed that the universe can be understood as a quantum computer. Not a computer in the everyday sense, with circuits and screens, but a system that processes information through physical interactions. In this view, every interaction between particles, every exchange of energy, every quantum event, can be seen as a computational step. The state of the universe evolves according to the rules of quantum mechanics, much like the state of a quantum computer evolves according to its programming. Lloyd even estimated the total computational capacity of the observable universe. Based on the number of particles and the energy available, he suggested that since the beginning of the universe, it has performed on the order of 10 to the 120 elementary operations. This is an enormous number, far beyond anything we can directly imagine. But it provides a way of thinking about physical processes in terms of information processing. In this framework, the laws of physics are not just rules governing motion and forces, they are rules governing how information can be stored, transformed, and transmitted. Information itself becomes a physical quantity. This idea is supported by several key principles. One of them is Landauer's principle, proposed by Rolf Landauer. Landauer showed that erasing a bit of information has a physical cost. Specifically, it requires a minimum amount of energy to be dissipated as heat. In words, this can be expressed as the minimum energy required to erase one bit of information is equal to Boltzmann's constant multiplied by temperature and the natural logarithm of 2. This principle connects information directly to thermodynamics. It shows that information is not abstract in the sense of being detached from physical reality. It has measurable consequences. Another important idea comes from quantum error correction. In classical computing, error correction involves detecting and fixing mistakes in stored or transmitted data. In quantum systems, this becomes more subtle, because quantum states are delicate and cannot be copied directly. Despite this, physicists have developed quantum error correcting codes that protect information by distributing it across multiple components of a system. What is particularly interesting is that these ideas have found unexpected connections to the structure of space-time. In certain theoretical models, especially those related to the holographic principle, the geometry of space can be described using concepts from quantum error correction. The way information is encoded and protected in a quantum system can correspond to how regions of space are connected. This suggests that space-time itself may emerge from patterns of information storage and correction. Rather than being a fixed stage, space could be a consequence of how information is organized. This is a subtle idea, but it aligns with the broader theme that has been developing. Properties, distances, and even the structure of space may not be fundamental. They may arise from deeper informational relationships. In this context, constraints on information play a crucial role. Quantum mechanics places limits on how information can be copied, known as the no-cloning theorem. It also limits how precisely certain quantities can be known simultaneously, as described by the uncertainty principle. These constraints shape the behavior of physical systems. They are not arbitrary restrictions, but fundamental features of the theory. They define what is possible and what is not. From this perspective, reality may be understood as a system that evolves according to rules about information. Particles, fields, and forces become ways of describing how information is arranged and how it changes. This does not reduce the richness of the physical world. Instead, it provides a different lens through which to view it. A lens in which structure arises from patterns, and where interactions are processes that transform information from one form to another. It also offers a way to connect different areas of physics. Thermodynamics, quantum mechanics, and gravity all involve concepts related to information. Entropy measures the number of possible configurations. Quantum states encode probabilities. Black holes appear to store information on their boundaries. These connections suggest that information is not just a convenient concept, but a unifying principle. As we reflect on this idea, the universe begins to take on a slightly different character. Not as a collection of objects moving through space, but as a dynamic system of relationships, constantly processing and transforming information. This does not mean that the universe is literally running a program in the way a human-made computer does. There is no external programmer, no predefined code. Instead, the laws of physics themselves define the rules of the process. The computation is not separate from the universe, it is the universe, and within this process, the structures we observe, particles, atoms, stars, and galaxies, emerge as stable patterns. Patterns that persist because they are consistent with the underlying rules. In this sense, reality may arise not from the existence of objects alone, but from the constraints on how information can be arranged and how it can evolve, a set of possibilities shaped by rules, giving rise to the world we experience. And while this perspective may feel abstract, it offers a kind of coherence, a way of seeing the different pieces of physics not as separate ideas, but as parts of a larger framework, a framework in which information, interaction, and structure are deeply intertwined. And in that quiet interplay, the universe continues to unfold, not just as matter in motion, but as information in transformation, guided by rules that are both precise and, in their own way, quietly elegant. As all of these ideas begin to settle together, the sense of strangeness that surrounds quantum physics starts to feel a little more understandable. Not because the concepts become simple, but because their origins become clearer. The discomfort does not come from the theory being inconsistent or poorly understood. It comes from a mismatch between the way our minds expect the world to behave and the way the world actually behaves at its most fundamental level. From the very beginning, human perception has been shaped by survival. We evolved to navigate a world of solid objects, predictable motions, and clear cause and effect. Our senses and intuitions are tuned to the scale of everyday life. Distances we can walk, times we can experience, objects we can hold. At this scale, classical physics provides an excellent approximation. Objects have definite positions. They follow continuous paths. Events unfold in a sequence that feels natural and intuitive. But as we move away from this familiar scale, the assumptions that support our intuition begin to lose their reliability. At the microscopic level, particles do not behave like tiny versions of everyday objects. They do not follow precise trajectories. They do not carry fixed properties at all times. They exist in superpositions, evolve through probability amplitudes, and interact in ways that depend on context and information. This is where the first layer of strangeness arises. We're trying to understand a domain of reality using concepts that were never designed for it. The categories of wave and particle, position and momentum, before and after, these are tools that work well within certain limits, but they are not fundamental. Quantum physics reveals that these categories begin to blur when examined closely. The second layer of strangeness comes from scale. The effects of quantum mechanics are always present, but they are usually hidden at larger scales. For example, the wavelength associated with a moving object becomes smaller as its momentum increases. For something like a human body, the wavelength is so small that any wave-like behavior is completely undetectable. This is why classical physics appears to work so well. It is not wrong, but it is incomplete. It is an approximation that emerges from the underlying quantum structure, much like a smooth curve can emerge from a large number of tiny steps. As we look more closely, those steps become visible, and with them, the simplicity of the classical picture begins to give way to something more intricate. Another source of strangeness lies in the role of mathematics. Quantum mechanics is built on a mathematical framework that does not correspond directly to everyday experience. Wave functions exist in Hilbert space, a high-dimensional abstract structure that cannot be easily visualized. Probability amplitudes interfere with one another, leading to outcomes that depend on the combination of possibilities, not just individual events. The mathematics is precise and consistent, but it does not always translate into intuitive images. This can make the theory feel distant, as though it is describing something abstract rather than something real. And yet the predictions derived from this mathematics have been confirmed again and again, often to extraordinary levels of accuracy. This suggests that while the mathematical language may feel unfamiliar, it is capturing something essential about the structure of reality. Information adds another layer to this picture. As we have seen, many aspects of quantum theory can be understood in terms of how information is created, transferred, and constrained. Measurement becomes an exchange of information. Entanglement becomes a shared informational structure. Even space-time may emerge from patterns of information. This perspective shifts the focus away from objects and toward relationships. Reality becomes less about what things are and more about how they are connected. This can feel strange because it challenges the idea of independent, self-contained objects. Instead, it suggests that the properties of a system may only exist in relation to other systems. And then there is the question of interpretation. Quantum mechanics does not provide a single, universally agreed upon picture of what is happening beneath the mathematics. Different interpretations, such as the Copenhagen interpretation, Bohmian mechanics, and the many-worlds interpretation, offer different ways of understanding the same formalism. Each interpretation is consistent with the experimental data, but they differ in how they describe the underlying reality. This plurality of interpretations can give the impression that the theory is incomplete or uncertain, but in another sense, it reflects the richness of the framework. The mathematics provides a stable foundation, while the conceptual picture continues to evolve. Taken together, these factors create the impression that quantum physics is strange. But this strangeness is not a sign of confusion or failure. It is a sign that we have moved beyond the limits of everyday intuition. The theory itself is internally consistent. Its equations are well defined. Its predictions are precise. Its principles are clear, even if they are not always easy to visualize. The challenge lies not in the theory, but in our expectations. We expect the world to behave in ways that align with our experience. When it does not, we describe it as strange. But from another perspective, the world is simply being itself. It is not obligated to match the patterns we find comfortable. In this light, the strangeness of quantum physics can be seen as an invitation to expand our understanding, to let go of assumptions that no longer apply, and to explore new ways of thinking about reality. It suggests that the universe is not limited to the forms we're used to. It is more subtle, more interconnected, and in some ways more elegant than the classical picture would suggest. And perhaps, as we become more familiar with these ideas, the sense of strangeness begins to soften. Not because the concepts become less surprising, but because they begin to feel more natural within their own context. What once seemed impossible starts to feel like a different kind of logic, one that operates quietly beneath the surface of everyday experience, a logic that does not replace the world we see, but supports it, giving rise to the patterns and structures that make our experience possible. And as we approach the end of this exploration, it becomes clear that the question is not why quantum physics is strange. It is why we expected it not to be. Because in a universe as deep and intricate as this one, perhaps a certain degree of strangeness is not only inevitable, but necessary.